session. So yeah, just a quick word from your sponsor, if you will. Take a look at that list. Two things I want to highlight in particular. First of all, up at the top on the articles, we have two blog sources. And if you haven't started reading SQLperformance.com, you're really well advised to do so if you want to take your skill level to the expert degree. Paul is one of the writers there. We have many of the best known individuals in the SQL Server community, the top experts writing on that website. The other thing I want to point out is kind of a two-part. It's under the downloads and the services boxes there. So one of the downloads you can get is Plan Explorer, and that is our free query tuning and advice product for working with SQL statements. Now on top of that, on the services box there is a website that is intimately linked with Plan Explorer. It's called answers.sqlperformance.com. So if you are using Plan Explorer, it makes it much easier to tune your SQL statements. It's completely free. We don't even ask for an email address. And there are hundreds of thousands of users. It's a very popular product. But on top of that, there's a button inside of Plan Explorer you can press that will load the query that you're trying to tune up to the website, answers.sqlperformance.com, and we will give you free help tuning that query. So just a little hint of what we do, and we're all about community, and we are passionate about SQL Server. So I hope if you're looking for SQL Server monitoring products, alerting and performance tuning products, that you'll give us a try. Thanks very much.
Thanks, Kevin. Quick virtual chapter news or virtual group news with the new naming. Shane O'Neill is our newest member, and he's helping with social media. We have a new Slack channel, and you can sign up here at https://sequelps.io/Slack. If you need to have any questions about it, you can tweet Shane at SOZDBA. Mark Swafford, our original, the guy that originally started DBAFundamentals, was going to be with us today, but he had something else he needed to take care of, so we'll probably get him in the next one. PASS has tons of virtual groups, and Paul in SQL Skills has been speaking at 80% of them.
We've had quite a few of these, yeah.
That's what I thought. But there's also virtual groups in other languages. So go to pass.org and join PASS and pick out all the different groups that you'd like to be a part of. Pass.org has officially launched. It's a refresh of the website, so go there and try to. It's sort of optimized for learning, and they realized that they needed to do a little bit more with the local and virtual groups and make the videos and the training that we have more available. So you can do that. Give it a try. Here's some of our meetings coming up. Down under, we're going to be doing an in-memory OLTP. SQL Skills, Jonathan Cass will be doing deadlocking for mere mortals. Dr. DMV's Troubleshooting Toolkit, Glenn Berry, and then Glenn Berry doing another Down Under session. And then we've got Brent Ozar. This is like a murderer's row, including Aaron, Kimberly, and Paul. So I hope you realize that you've got some great speakers, or there's some great speakers coming up. Please be sure and sign up. Oh, at the end of March, we'll be giving away half of the amount of money that we have from Century One to give away as an Amazon gift card for everybody that's attended sessions, either in Australia or in the U.S. through the end of March. Then we'll start off with the same thing in April. Other select virtual meetings. The Women Technology this month is doing a special series, which is fantastic. They'll be having Erin Stellato with SQL Skills. She's fantastic. Her and Jonathan are just probably the best people in the world on extended events. Saturday Night SQL will be reporting on SSRS 2016 mobile reporting. Kaylin Delaney will be doing seeking SQL Server secrets, and Ree Irish will be doing a session on identifying and understanding gender bias and inequality. SQL Saturdays are a mini pass session in one day at someplace probably close to you. You can go and get free training all day and pay for your lunch, and that's about it. Go to SQLSaturday.com and you can check and see which one is closest to you. The recordings will be, this session will be recorded, and you can reach that here from fundamentals.sql pass, or you can go to our YouTube channel, and you can subscribe and you'll be notified when we upload it. The attachments will be here. Okay. I've already mentioned that Paul Randall is presenting today. I'm not going to spend a lot of time introducing you to Paul Randall, because if you've been in SQL for very long, you already know that he's probably one of the top DBAs and DBA trainers in the world, along with his wife, with SQL skills. He, well, I mean, I was telling somebody one time, and I was asking them, well, have you ever heard of DBCC? And they said, sure. He said, well, he wrote that. So that kind of tells you he was with Microsoft for a long time and helped develop the engine and worked with it, and still is very intense into it, and the training from SQL Skills is unbelievable. Anyway, let me just turn it over to Paul. I know that wasn't smooth, but let me make you presenter, Paul.
Sure. You see that?
Looks good to me.
Perfect. Okay, I'll take it away. Thank you, Steve, and as always, thank you for the opportunity to present to such a wide audience. Now, as Steve mentioned, he's recording the session, and when I'm done talking, I'll produce a PDF of these slides and a zip file of all the demos that you're going to see, and he'll upload that and make that available to you all as well. So, perf troubleshooting using weight statistics, one of my absolute favorite topics to talk about. Got a couple of slides just to talk about SQL skills first. List of all the people that work for us. You probably recognize some of those names. We do training, consulting, blah, 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 blah. We have a bunch of classes coming up in Chicago. That's our main event. We have like 10 classes coming up in Chicago. Bellevue in September and Chicago in October. I'm going to release those later on this week. A whole bunch of different courses. We have a new course on PowerShell coming in May, and we're also having new courses on Azure, and then upgrading to SQL Server 2016 coming up in October. That's going to be really cool. If you're interested in any consulting services, we have a nice discount that we like to offer people. You can get more information using the links on that slide there. And then me, I used to work for the SQL team for about 9 years. I left about 10 years ago now, actually, in August. It's pretty amazing how time flies. But the interesting things on this slide, my email address. If you have any questions about weight statistics that you don't get a chance to ask during the session today, by all means send me an email and just say pass virtual group question, and I'll see what I can do to answer the question for you. On our blogs, we'll blog an awful lot on SQL skills. There's tons and tons of information out there in the SQL community, and also Twitter has a very, very vibrant SQL community as well. If you've never tried that, I encourage you to try that. And one last thing before we get to the actual technical content, we have a whole bunch of online training through a company called Pluralsight. We actually have about 150 hours now with 50 courses. If you would like to try that out completely for free, there's no catches, you don't have to give a credit card or anything at all, then shoot me an email saying use a group Pluralsight code or something like that, and I'll send you a free pass for 30 days to listen to me or anybody else from SQL Skills. And incidentally, one of the courses on there is a 4.5-hour deep dive into the stuff we're talking about today, with information on latches and spin locks, which we don't have time to go into in a constrained session like this one. Okay. Now, as far as questions are concerned, every 5 or 10 minutes or so, I'll stop and ask Steve, hey, any questions? And he'll read out the questions, because I only have one screen. I present off a laptop in a sound booth, so I don't want to have all the questions popping up while we're presenting and distracting you all. And feel free to ask any questions at all. So one of the things that I find when I'm either consulting or teaching people or even just working with a client or just email that I get from people is people tend to do what I call knee-jerk performance tuning, where they've been asked to do some kind of perf troubleshooting and they see a symptom and they knee-jerk and say, aha, that symptom means it must be that. And so they go down a path of troubleshooting that particular thing, and very often that's not the actual root cause of the problem. What you need to be able to do is take a symptom that you're seeing and figure out where to go looking to figure out what the root cause of the problem could be. One of the best ways to do that is to use something called weight statistics, which SQL Server provides for you. So what we're going to cover over the next 75 to 90 minutes is I'm going to talk about what weights are. We're going to look at how the thread scheduling works inside SQL Server. That's the thread lifecycle, because that's integral to understanding weight statistics and how they work. We'll talk about exactly what weights are. We'll look at the various definitions, the nomenclature around weights, the wait times, the various DMVs you can use. I'm going to walk you through what some of the very common weight types that you're going to see on your systems over and over and over again. And I'll do a bunch of demos as we go along. So again, don't assume that the symptom is the root cause. Okay, so I'm sure that many of you listening today have seen IOs taking a long time. So reads, for instance, taking a long time. And one of the things that people knee-jerk when they see that is, oh, there must be something wrong with the IO subsystem. And most of the time, that's not the case. Now, it's true that if your reads are taking too long, the IO subsystem is probably overloaded. That doesn't mean there's something wrong with the IO subsystem per se. It means that SQL Server is driving more reads than the IO subsystem can handle. You know, if you've spec'd it out to do a certain number of IOPS, and now the IO subsystem is being driven at twice that, it's going to go slower than you'd like. So what you really need to do is take a step back and say, why is SQL Server doing so many reads? And that could be something as simple as a catastrophic plan change. So for instance, something that was doing small targeted index seeks is now doing a parallel table scan. Or it could be that the amount of memory available to store data file pages, basically with the buffer pool, has shrunk. Why could that have happened? It could be that the SQL Server process is under memory pressure, and so it's had to give back some memory to Windows for some other executable, and so it's the buffer pool that shrinks. It could be maybe that somebody has inadvertently turned off optimize for ad hoc workloads in the SP configure settings, and then you've had a storm of ad hoc queries that have come in that have bloated the plan cache. All that plan cache memory is borrowed or stolen from the buffer pool. Or it could just be that the volume of your data has grown and you've reached a tipping point where it can't all be held in memory. Your basic working set of data can't be held in memory, and so SQL Server is having to drive reads. So don't knee-jerk and assume that whatever symptom you're seeing must be the absolute root cause. And I'll reiterate that a few times as we go through some of the weights as we go along. So if you've never used weight statistics before, as with any new thing, there's a learning curve. And the learning curve with weight statistics is short and steep. Okay. It's short because once you've done them a couple of times, in fact, once you've watched me do it a few times, hopefully you'll have an idea about what they are, how to get the data back, and some of the interpretation of the data. Okay. So using weight statistics, the first thing you have to know is how to get the data back correctly. Okay, there's two DMVs that I'm going to show you, and you can't just do select star from the DMV. As with many DMVs, you can't just do select star. You have to do some post-analysis or joining with other DMVs to get really actionable data. You also have to understand what some of the common weight types mean, because there's a subset of all the weights that you're going to see over and over and over and over. And you want to know what those are actually telling you. You also want to know what they're not telling you. Now, what do I mean by that? There's all kinds of advice out there on the internet, and unfortunately, a lot of advice around SQL Server in terms of anything to do with SQL Server is incorrect. It's not that people are malicious and they've written deliberately incorrect information. It could be the information in a blog post or article is out of date, or maybe the person didn't understand what SQL Server was doing, or maybe they saw this particular thing in one scenario and they extrapolate that out to be, oh, this is a best practice or a generalization for everything. Okay. And some of the most egregious advice I've ever seen around weight statistics is, oh, if you're seeing CX packet weights, set your max DOP to 1. No, it's a horrible, horrible thing to do. And it shows a fundamental misunderstanding of what CX packet actually means. That's actually one of the weight types that I'm going to go into in great detail, and you'll know exactly what it means and when you should do something about it. There are also some patterns that you're going to see, and I'm going to show you some of the common patterns as we go through some of the demos as well. And then, just like any new thing, the more proficient you want to be, the more you've got to practice. Okay, so running the various weight statistics analysis, DMVs, on your servers, the more times you do that, the more comfortable you're going to be with that data, and more comfortable using that data to go and figure out where to go, digging deeper to figure out what your performance issues are. Now, rather than just having a single look at the data, okay, it's even better to have a series of snapshots of the data over time. And I'll show you a blog post that's going to show you how to do that. So that's going to allow you to do things like, let's say that somebody comes to you and says, hey, hey Bob, that at 2 o'clock on Saturday morning, we had reports from our users in Malaysia that the server here in the States wasn't performing very well. Any idea what could have been happening? If you don't have any historical data that you're capturing, the answer is going to be no. You're not going to have any idea. But let's say that you're capturing a snapshot of weight stats and maybe I/O statistics and maybe some perf1 counters every half an hour, and you keep that data around for a couple of weeks. You can go back and do some time series analysis over, say, Friday evening leading up to Saturday at 2 o'clock and figuring out, oh yeah, look, it seemed like we were seeing this and this were happening, so maybe I'll go and have a look and see what was going on there. Okay. And the other thing to mention, I don't have this on a slide, is you can use T-SQL scripts to do weight statistics analysis. It's completely free. You'll also find that all the major performance monitoring third-party tools, for instance, SentryOne's tools, will do weight statistics analysis for you and capture the series of snapshots and aggregate them over time to allow you to have a little graphical dashboard and an easier, potentially easier way, if you're not so proficient with SQL Server, to have a look and see where there might be a problem. So what are weights? A weight is when a thread is processing, is running SQL Server code, and it comes across a resource that it needs to acquire, and it can't acquire the resource. And it has to stop and wait till it can get that resource. Here's an example. Let's say there's a thread in the storage engine running access methods code, and it needs to acquire a lock on a certain page in an index. So it calls into the lock manager, and now the thread's running lock manager code, and it looks in the granted list for that particular resource and sees that somebody already has an exclusive lock on that page. Kind of a rare situation, but somebody has an exclusive lock on that page, and it wants, let's say, a share lock. So it has to put itself onto the pending queue for that lock, and it gets suspended. I'll talk about what that means a little bit later. And now it has to wait until it is told that it now has that lock. Okay. The thread absolutely can't just skip over that resource requirement to carry on running. It has to wait. So the fact that that thread had to wait is tracked by SQL Server. SQL Server tracks the fact that A, the thread waited, B, what it's waiting for, C, how long it actually has to wait for the resource. And the aggregation of all that wait information is very useful to us. Because if we know what our weights look like when everything's running normally, if we have a performance baseline, then we can compare that baseline to how things look when performance is kind of crappy. And we can see what the difference is, and that's going to give us clues about where to go looking for deeper information. Even if you don't have a baseline, which is always really good to do, you can still glean information from weight statistics. Okay. So some examples of resources that may be unavailable. So the first one is the lock case that I said. So the weight type that you're going to see is LCK_M_something, where you see in the slide deck XX. That's me saying that could be a variety of different things. Maybe X for exclusive, or IX for intent exclusive, or more rare ones like _RS_something for a lock that's in the serializable isolation level. So that stands for lock mode something. And then let's say that a thread wants to read a copy of a page from disk. The weight type that you're going to see is this one, page IO latch _something. I'm going to talk about all these in a little bit more depth as we go along. Waiting for a page to be read in from disk. And if this is SH, that means it's just the page is just going to be read. If it's EX, that means the page is going to be changed. Results from part of a parallel query. Right? CX packet, that's the name of a C++ class inside the query processor to do with exchanging packets of information between threads in a parallel operator. We're going to talk about exactly what that means as we go along. And then this one here, we're not going to talk about, we don't have time. This is every data structure inside SQL Server is protected from multi-threaded access. And the way that's done in most cases is by a mechanism called a latch. You can think of it as a very lightweight lock. So sometimes you might have contention for a particular data structure, and you might a non-page data structure, and then you might see the wait type is latch underscore something, and you're going to go and have to look at latch statistics to go and see what particular latch is the problem. As I said, we don't have time to go into that, but I'll point you at resources at the end of the deck. I've got blog posts that talk about that. There's a white paper that talks about it, and of course my Pluralsight course talks about it as well. So Steve, any questions so far?
No.
Okay. You're supposed to spin it out a bit longer. This is how I take my drinks as I ask you about questions as well.
Okay, I'm sorry.
No, that's okay. I'm just kidding. All right, so carrying on. Thread scheduling. SQL Server does all its own thread scheduling. Now, SQL Server is running on top of Windows, so there is obviously the Windows scheduling that's happening as well, Windows Server scheduling. Windows Server scheduling is pretty complicated compared to SQL Server scheduling. Now, if you try to start thinking about, well, SQL Server scheduling within the confines of Windows scheduling, so how does that all work? It gets extremely complicated really quickly. So what I advise everybody to do is ignore Windows scheduling. Assume that SQL Server is the only thing running on the Windows box, and that just simplifies the whole how to think about how thread scheduling works. So SQL Server does its own thread scheduling, which means that Windows can't tell SQL Server what to do with its threads. And this is called non-preemptive. In other words, Windows can't preempt SQL Server. There is an exception to this when a SQL Server thread has to call out to Windows, to some Windows API. In that case, the thread is now running Windows code. And so it has to switch to preemptive mode, where Windows does control what's happening with that thread. But let's assume that the thread doesn't do that. So the thread's running on a thread scheduler. And every logical or physical core on your server has a thread scheduler, depending on what edition you're running on, how many cores you can use, whether you've got CPU masking, and so on. For instance, my laptop that I'm doing this presentation on has one physical CPU. That CPU has 4 physical cores, and I have hyperthreading enabled. So I have 8 logical cores. There are 8 what are called user schedulers for processing whatever I ask SQL Server to do. There are a couple of background schedulers for background tasks for the dedicated admin connection, but there's basically 8 for me to do my processing, or SQL Server to do what I want it to process. Okay. The scheduling is done by the threads themselves. There is no thread per scheduler that does the scheduling of everything else. So the threads are basically doing cooperative scheduling amongst themselves, which is kind of an interesting thing. There is obviously a background thread that monitors to make sure there aren't any scheduling issues, but the threads handle everything themselves. Okay. Now, where do these threads come from? When SQL Server starts up, it does a calculation based on the number of cores and so on to figure out how many threads to create. And I believe my thread, on my laptop, on my instance here, is going to create 584 threads. Those threads, the worker threads, are put into a thing called the thread pool. When a query executes, query execution figures out how many threads are going to be required for this particular query, takes the threads out of the thread pool, distributes them amongst the schedulers based on your max DOP setting, and then the threads stay on those schedulers until they're finished processing, and then they go back into the thread pool. It is, of course, possible to run out of threads, in which case you're going to see all one word thread pool waits occurring. That could happen, for instance, where you've got a very wide parallel query and several hundred connections all come in and try to start running it. You're going to very quickly run out of threads. Or a thread comes in, a connection comes in, acquires a lock on something, and then hundreds of other connections all come in, and they all want the same lock. You're going to run out of threads as well. And that might manifest as thread pool waits. Also, you can't log into SQL Server. There's no thread available to process the login request. So the basic components of a scheduler, there's 3 parts to a scheduler. You've got the processor, and only one thread can be running on the processor itself. You've got the waiter list, where all the threads that are waiting for a resource are sitting. And then you've got the runnable queue, where all the threads that have their resource but just haven't got back on the processor are sitting. And threads basically go round and round in this clockwise fashion as the arrows indicate until they finish processing the query. We're going to look at the transitions between these various parts of the scheduler. Your threads can be in one of 3 states: running, suspended, and runnable. Very obvious what they're doing there. Running is on the processor, suspended is waiting for a resource, and runnable is on the runnable queue. And these states you're going to see in various DMVs, dealing with exec requests, things like sys processes and stuff like that. So going from running to suspended. Okay, so a thread is running along and it comes across the need. In this case, for example, we're going to need to read a page into memory. So this is a thread in the, let's say, the access methods portion of the storage engine has called into the buffer pool and it's running buffer pool code to see whether a page is already in memory. If the page is already in memory, that's called a logical I/O. It completes immediately. The thread pops back out into the access methods code and continues running. But if the page isn't there, then the thread has to initiate a physical read. So it kicks off the physical read, and that's called a physical I/O, and the thread has to wait until the I/O completes. So the wait type is page I/O latch share, and it goes to the waiter list. Now, as soon as it vacates the processor, whatever's at the top of the runnable queue goes up to the processor. Our thread is sitting now on the waiter list, and it will sit there until it's told that its resource is available. There is no limit to how long it can wait on the waiter list. There is no limit to how many threads. There's no practical limit to how many threads can be on the waiter list. And there's no ordering on the waiter list. It is a list, not a queue. A queue is ordered in computer science terms. A list is generally not. And so any thread on the waiter list can be told that its resource is available at any time. It could be the most recent thread that entered the waiter list. That's the first one off it. It entirely depends on what the various threads are waiting for and what else is going on the server. So another couple of questions that I often get asked about the waiter list. What if there's two threads on the waiter list for a single scheduler that are waiting for exactly the same resource? Which one gets told first? Which one gets unsuspended first? And the answer is whichever one started waiting for the resource first. It is not possible for two threads to start waiting for the same resource at exactly the same time. Okay? Even if, let's say, you've got two threads on different schedulers trying to get the same lock, they can't actually wait for the lock at the same time because they both have to insert themselves onto the pending queue for that lock. And that pending queue is managed by another synchronization process called a spin lock. Only one thread can get the spin lock. So one of them is going to win the race, if you will, to get onto the pending queue first. And so everything is ordered inside SQL Server. So go back to the original question. Whichever thread entered the waiter list first, that's the one that's going to be essentially popped out onto the runnable queue. Okay, and I actually answered the second question as well, because the second question I was going to say was, what if they're on different schedulers? So I already answered both those questions. Now going from suspended to runnable. Let's say that the thread's sitting there on the waiter list. How does it know when its I/O completes? Well, you might say, well, it can look every so often and see whether its I/O completes, but it can't. Because to be able to look or poll, P-O-L-L, to see whether the I/O has completed, it would have to be running code. And to do that, it would have to be on the processor, and it's not on the processor, so it can't run any code. So this is where the kind of cooperative scheduling comes in, because some other thread has to help out the scheduling here. Some other thread is going to notice that the I/O completed and will signal our thread by moving it to the bottom of the runnable queue. Okay, which is very interesting. So our thread doesn't know. I mean, obviously our thread doesn't know anything because it's just a thread. Our thread doesn't know that it's been signaled until it gets back up onto the processor. Now this other thread, it could be some thread that's just about to be moved onto a waiter list and is able to run a little bit more code. It will go in and help out the buffer pool by looking to see if any IOs have completed and complete one of them by running what's called the IO completion routine, which will move the thread that started the IO to its runnable queue on its scheduler. And there's all kinds of addresses involved so that various threads know where the other ones are. Similar thing happens for the lock manager. So if there's a thread sitting on the pending queue in the lock manager and the thread that currently has the lock granted is going to drop the lock, it has to look on the pending queue to see whether there are any threads that it can now help grant that lock to. If the answer is yes, it moves that thread's entry to the granted list and signals that thread on its scheduler that it is now runnable. Okay, and this process is called being signaled. Okay, and once the thread moves to the runnable queue, it is now runnable. Nothing is stopping it running apart from the fact that it hasn't yet bubbled up to the top of the queue and got on the processor. Now the runnable queue is a true first in, first out queue. Okay, it's called a FIFO queue. But there is a twist. Right? There's a twist with Resource Governor where you can assign priorities to different workload groups within a resource pool. I've never seen it actually used in production, so ignore that. There's also a twist in 2016. The scheduling mechanism changed a little bit in that the way the runnable queue works is a thread may not go to the end of the runnable queue. It might go a little bit higher up. And that's because they've changed how scheduling works for some workloads to try to get more of a balance of processor time between the threads that are on a particular scheduler. So there isn't one thread that's able to run, and then get off, and then another thread that is only able to run for a tiny amount of time and then get off. So they try to balance that out. Okay. Now, talking about that, there is a limit to how long a thread can run on the processor before it must get off the processor. It's called the thread quantum. It's fixed at 4 milliseconds. It's always been that way. It's not changeable. I don't imagine it changing anytime in the future. So after 4 milliseconds, the thread has to get off the processor. It does this voluntarily. It has to call into SQL OS and say, hey, how long have I been running? Do I need to get off the processor? And if the answer is yes, it gets off the processor, but it goes directly to the bottom of the runnable queue because it's immediately runnable again. When this happens, it has to register a wait, and that wait type is SOS scheduler yield. The thread yielded the scheduler. Now, some people say this is a sign that you need more CPUs, and that's incorrect. That is a sign that you've got a workload where threads are able to run without having to stop for a resource. And that could be perfectly valid. It could be that you've got a table that's in memory and you're scanning it, and your workload does that. It doesn't necessarily mean you need to add more CPUs. If you find that the rest of your workload is slowing down and you've got a lot of SOS scheduler yields, then you might need to add more CPUs. But the fact that you've got this wait type in and of itself doesn't mean add more CPUs. It's that and other things that might enable that. So that's going from suspended to runnable. Going from runnable to running, very simple. Whatever's at the top of the runnable queue when the processor becomes vacant moves up and now is running. And the cycle continues. Okay. So the various points that the thread might stop have wait times associated with them. So there's the overall wait time, which is I'm on the processor going round to I'm on the processor again. So that covers going through suspended and runnable. Now, when most people talk about wait time, they don't mean that overall wait time. They mean the resource wait time, because there's two components to the overall wait time. There's how long did the thread stay suspended, and how long was it runnable. And the runnable time is usually very tiny. Right? There are times when that could be more than 1 or 2 milliseconds, and there are cases you could troubleshoot that, and we don't have time to go into all the cases today. I talk about that more in the ProSite course. The resource wait time is generally the long time, and that's why most people, when they say wait time, really mean the resource wait time, and you'll hear me saying that through the rest of the session as well. So graphically, if we've got a thread sitting on the processor and it gets suspended for whatever reason, it moves down to the waiter list. It sits on the waiter list until it's signaled. And so when it's signaled, it moves to the runnable queue. All the time in red there is the resource wait time. It goes to the bottom of the runnable queue, let's just say, and then bubbles its way up to the top of the runnable queue and gets onto the processor, hopefully very quickly. All that time in yellow is the signal wait time. And adding those two things together get us the overall wait time. So Steve, how are we doing? Any questions so far?
Yes, we've got quite a few. Are wait stats still valuable in Azure SQL database environments?
Yes, they absolutely are. There's a different DMV you have to use from sys.dmos wait stats. I think it's sys.db wait stats. If you look on century1sqlperformance.com, look for an article by Tim Radney, and he talks about how to do wait statistics and IO statistics analysis on Azure, and how to change the various scripts that I'm going to give you to work perfectly on Azure. But yes, they are absolutely valuable.
Good deal. I didn't even know about that.
Yep.
Are wait statistics different on VMs with SAN storage from physical servers?
The interesting thing about wait statistics on a VM is that if you have CPU ready time issues where the VM is not able to run for a few hundred milliseconds or maybe a couple of seconds, you'll see your wait times be longer, because the wait times are based on the essentially the system clock. So if your VM pauses for a bit, all the waits pause too, and you get more wait time added on. but how you use weights is exactly the same on a VM, no matter what the underlying storage is, as you would on a physical server with whatever the underlying storage is. Just be wary of that CPU ready time issue.
This is sort of an outside question. Does thread scheduling in SQL Server work the same when ran on Linux?
I have no idea how they do it under the covers. I would imagine that the actual scheduling, all the stuff that I'm talking about, is the same. The underlying processor primitives that they're using are going to be different. There's a layer called SQL OS, which sits between all the rest of SQL Server and the underlying operating system. And that is responsible for running what SQL Server does using whatever operating system primitives and processor primitives the underlying system has. So I would say that everything I'm talking about is the same, but it might be implemented slightly differently. I haven't dug into it in great depth to know if there's anything that would affect how you would process wait times. My gut feel would be there isn't, because that would be a wholesale paradigm shift that I don't believe the SQL team would want to have.
Okay, we've got a couple of questions on what is the status sleeping when you do SP-who2, and
sleeping is, if I remember, sleeping is probably it's waiting for you to do something. So you've got a connection to SQL Server, it's not currently running anything. So it's just sitting there waiting for you to say do something. I haven't used SP-who2 for a very long time, so I'm hoping that is correct.
Okay. What happens to the waiter list if the originating query is killed or canceled?
So if the originating query is cancelled, this is very interesting. Remember, the threads will all get back onto their runnable queues. They'll get back up to the processor, and eventually they'll make a call into SQL OS saying, do I need to get off the processor or have I been killed? So if the thread is killed, there's actually no way to kill a thread. There's no way to kill a SPID. What you do is, when you do kill SPID, it notifies all the threads in their thread local storage that the SPID has been killed, and then the threads are responsible for killing themselves. So this is why, for instance, if you have a thread that's sitting on the processor, just spinning and spinning and spinning and spinning, you try to kill the SPID, it doesn't die. And you get what's called a non-yielding scheduler. You get error message 17883 in your error log, because there is no way to kill a thread. The same bit of code that the thread calls to say, do I need to get off the processor, is the same bit that says you've been killed. So that's what basically happens. All the threads go back into the thread pool eventually.
Okay, how do you check the runnable queue?
If you want to look at the length of the runnable queue, you could look at sys.dmos schedulers, and that will show you all the schedulers you've got, both the visible ones, that's basically what they call the user schedulers, and the non-visible schedulers, so all the background schedulers, and then you can see how long the waiter list is, how long the runnable queue is for each of those schedulers.
How do we get internal details with what SQL Server is doing at the process or thread level for performance tuning?
This is what we're talking about in terms of weight statistics.
Overall. Okay.
Yeah.
Let's see.
And whoever asked that question, if there's more to it than that, shoot me an email. Okay, because you can't really get deeper. Well, the only way you could get deeper to see what the threads are actually doing is to attach WinDBG with debug symbols and watch as the thread actually moves through SQL Server's code. That's the only more depth you could do. Or you could use xperf to have a look and see what call stacks are being called and stuff like that.
How about the kill session that takes a long time to roll back?
That's just because if the transaction has made a whole bunch of changes, all those changes need to be undone. Slightly off topic because it's login and recovery, but you can't just kill a transaction that's made a bunch of changes. All the physical changes that the transaction's done need to be undone, so the logical effect of that transaction in the database is nothing. The physical effect of the transaction is still all the pages changed twice, once on the forward part of the transaction and once to roll back all the changes again. So that's why it could be taking a long time. Also, if your transaction log has a huge number of virtual log files, the search backwards through the transaction's log records can take a long time the more VLFs you have, and that's a well-documented phenomenon as well.
One more question. There's this user wants to know if there's waiting stats and DMVs for threads waiting in a runnable queue.
For all the threads that you've got, you can see where they are, and you can see whether they're on the waiter list, whether they're on the runnable queue, and you can tell how long each thread's been sitting there on the runnable queue. However, you're generally not going to be able to see threads on the runnable queue because they're only going to sit there for less than a millisecond or maybe 1 or 2 milliseconds, which is why it's way, way easier to look at the aggregate wait times and see what the average runnable time is for a scheduler or for a particular wait type.
Okay, there's a question about SharePoint, but that might be something better emailed to you. And okay, let's go.
All right, cool, thank you. So the 2 DMVs that you can use. The first one is DMOS waiting tasks, and I call this the what's happening right now DMV. Although to be more technically accurate, it's really the what's not happening right now, because this is showing you a list of all the threads on all the waiter lists for all the schedulers. Okay. And so this thread and this DMV, I'm not going to run through all the stuff that it shows you. I'll show you when we do the demo in another few slides. This DMV is very useful thing to run. This is going to be one of the first things that I will run, the script containing this DMV, when I walk up to a SQL server that is performing poorly. Because this is very often shows a pattern of that you can interpret and see what might be an immediate issue that you could have a look at. Okay. Now, this DMV on its own, if you just do select star, there's a whole bunch of extra data that you don't need, that's not actionable, and you really want to join it up with a bunch of other DMVs to get some really cool output, and I'll show you that when I show you the script. And then the second DMV, DMOS wait stats, this is the what's happened in the past. And there's actually an analogy here between wait statistics and IO statistics, because this previous one, there's sys.dm IO pending IO requests to look at what outstanding IO requests you have. And then there's DM IO virtual file stats, which shows you an aggregate of all the IOs that have happened. So you can see what's happening now and what has happened, both the wait statistics and for IO statistics as well. Let me just break out here to my blog. And on my blog, this is my blog talking about wait statistics in the category. If you go back a little bit, there's 2 blog posts here from the end of 2014, how to capture wait stats for a period of time and how to capture IO latencies for a period of time. And both of these blog posts have scripts that will run for half an hour, and you can tweak that for whatever you want, and will allow you to capture those 2 very, very important sets of metrics that you can use to do time series analysis or baselining, for instance, based on those 2 DMVs that I just mentioned. So this is the what has happened in the past view of the server, and it shows you the aggregate of all the waits that have occurred since your server started or since you last manually zeroed out the wait statistics metrics, because you can manually zero them out, which is very useful for doing demos, as I'm going to show you. Okay. Now again, this DMV, if you just do select star, and I'll show you this, you get information for all the waits that exist on the server, even if they haven't been waited for, all the wait types I should say, even if they haven't been waited for. So on 2014, you're going to see me run this DMV, we're going to get 769 rows of output. Now you don't care about that, you want to see what's the most prevalent waits compared to everything else. So you're going to have to do some math and some processing on the results, and I'll show you that when we do a demo in a couple of slides. Now, as you've no doubt gathered by now, the way that SQL Server does its thread scheduling, waits always happen. And it doesn't mean that those waits are bad. Okay? Waits are always going to occur. So you need to figure out a couple of things. Firstly, you need to not look at the waits that always happen in the background and are benign. For instance, one called lazy write or sleep. You'll see there's a big list of wait types that I generally filter out because the vast majority of the time they're not a problem. I'm not going to say they're never a problem. Okay? But there are pathological cases for some of these background wait types. So lazy writer sleep, if there's no lazy writer activity based on pressure on the buffer pool, that thread's going to sit there and sleep for a long time. And that could be then the most prevalent in terms of overall wait time, wait on your server. Is there anything you can do about that? No, it doesn't mean anything. It's not a bad thing. So you should filter out those waits that could essentially pollute the output and stop you from seeing the really important stuff. And then with all the weights that are left over, you have to figure out whether it's worth caring about them. So for instance, imagine that over the course of a day, you had 1,000 weights show up for a share log. Is that a problem? There's not enough information there to be able to tell. You need to look and see for those weights, what was the average wait time for those weights. So let's say that for all 1,000 weights, the overall wait time added together for all 1,000 of those weights was 50 seconds. So on average, each one of those is 500th of a second. Is that something that would jump out as a big red flag that I need to go and look at first of all? No, probably not. But if every one of those 1,000 weights was individually 50 seconds, if I didn't know anything else about your workload, that would be something that I'd want to know about. Okay, so this is what I mean by the getting rid of the benign weights and making sure that you're looking at the top relevant weights. So talking about the top relevant weights, this is a survey I did a couple of years ago. And I put some code out on my blog and said, run this code, it'll run for 24 hours, capturing your weight stats, and then tell me what the top weight is. And I got information back from 1,700 random SQL Server instances across the internet, and I'm sure some of the people listening participated in that survey, and I thank you for it. Now, it was interesting because I'd done a survey similar about 5 years previously, and I was able to compare the results. Now, because this is like random people sending me random information about instances all over the world, I would go out on a limb and say this is a statistically valid sample of what's happening out there in the field. So it was actually interesting because I was quite stupid, and I said for this survey, if you give me all your information, I'll give you a Pluralsight code, and that wasn't stupid, but what I said was, and I'll tell you what every single one of your weight types mean, and give you a little bit of advice about them, and that was the stupid part, because I got back information from 650 people, and it took me about 3 months to reply to everybody, but I did actually reply to everyone. Now, it was worth it though, because I got confirmation that the top weight type, CX packet, hadn't changed in 5 years. Okay? In fact, most of this list hadn't changed. The big change was this guy. OLADB had jumped up from being down here in the weeds to up here, the number 2 one. So we'll talk about that in a second. Now, all of these down to here we're going to talk about through the rest of the deck. These 3 were not. I've already told you what SOS scheduler yield means, and I've got a lot more information. If you go to my weight stats blog, there's a couple of blog posts talking about this, and also on the century1sqlperformance.com, I have some blog posts. In fact, even better, let me show you this. Last May, I published this resource on our website. It's completely and utterly free. What this is a weight types library. It's the only place in the world this stuff is documented to this depth. It is every weight type that has ever existed and all latch classes that have ever existed since SQL Server 2005. And I've documented them, what they mean, what they don't mean, some more information about troubleshooting, and some example call stacks. And out of the 900 or so, I've done just over 300, including latch classes, and I'll actually be adding some more this week. So if we look for, let's go down and look for instance, CX packets. You'll get the page that comes up with CX packet. And you get the book's online description if one exists. You get my description of what it means, and then some information about where to go looking, more stuff to go reading, and then some examples of where it might actually occur inside SQL Server with what those examples actually mean as well.
This is an awesome tool. I just wanted to add that in because you can learn so much from weight stats when you go to this.
Thank you. Thank you. Yeah, it's very much a labor of love, and there are some people around the world. There's the most prolific contributor I want to give a shout out is a guy called Aaron Serpal in the UK, who's been to a couple of our classes, a really nice guy. And in fact, he just sent me a whole bunch more call stacks for stuff that I don't already have this morning. So if you're interested in helping collect call stacks for this, then shoot me an email, and I'll hook you up with what to do. Okay, it's non-trivial to be able to do this, but it's a cool thing, and your name will appear at the top here as the list of contributors, so your name will be immortalized there. Anyway, so I was talking about SOS scheduler yield. All the scripts that I'm going to get will automatically generate clickable URLs. So you can just click inside SSMS and it'll bring you up to the weight types library so you can get some more information about what those are as you're doing live troubleshooting as well. Now, backup I/O. This is where you're backing up to a slow I/O subsystem. For instance, maybe a tape drive or across a network. What it means is there's a thread in a backup operation that's waiting for a backup write to complete, so writing out to a backup file. And if you're seeing lots of backup IOs and you're doing a parallel backup where you're backing up from multiple drives or to multiple drives, then you might see backup buffer as well. This is where there's a thread in a backup operation that is waiting for a buffer to write information into to then write out to disk. So if the buffers are taking a long time to write, then you might have other threads waiting for buffers to become available. Okay. Now, going back up here, OLADB popped up in 5 years. Now, when most people see OLADB, they think, aha, linked servers. So do you think in the 5 years between my two surveys, a whole bunch of people across the world suddenly started using linked servers? No. What did happen was that there was a huge proliferation of third-party performance monitoring tools. And what many of these perf monitoring tools do is they sit basically running DMVs in a loop. So if the tool is sitting running DMVs, most of the DMVs are written as select star from open row set, name of DMV. So hopefully some of you are thinking, aha, open row set, that's using the OLADB mechanism under the covers, and that's exactly right. So if you're seeing OLADB be one of your top weights, have a look and see how much the average wait time is. And if the average wait time is, 1 or 2 tenths of a millisecond, and the number of OLADB waits is hundreds of millions or billions, then you've got a third-party performance monitoring tool installed. And I'll talk about that a little bit later on. So a couple more slides, and then we'll get into our first demo. So page IO latch waits. Okay, the knee-jerk reaction to this is, oh, it must be the IO subsystem. But no, remember what I said. I want you to go back and figure out why SQL Server is driving IOs. So you're going to be looking at what table the IO is going to. And I'll show you how you can do that from the wait information. There's also a pattern that you can look for, which is if you're seeing lots of page IO latch share waits and lots of CX packet waits, that generally suggests you've got a parallel scan happening. And so you might look and see where that's coming from in your query plan and say, do I expect there to be a big parallel scan happening, or should that be using an index? Now look, page latch, going back, page IO latch, page latch, page IO latch. In this one, there's no IO. The knee-jerk reaction to this wait type is, oh, it must be the IO subsystem, because people get confused between page latch and page IO latch. This wait type is contention for a page that's already in memory. Okay. For instance, there's a couple of classic cases. First one, classic tempdb contention. So if the page is in tempdb and it's an allocation bitmap, and the common one is 2:1 or 2:1:1 or 2:1:8088 or any multiple of 8088, it's an allocation bitmap. And that's from lots and lots of concurrent operations creating and dropping little temp tables with not enough tempdb data files. Classic tempdb contention. And another one, which I'm actually going to show you, is what's called an insert hotspot, where you've got a table, for instance, with a clustered index and an int identity column or a big int identity column, and the row size is pretty small, so you can get lots of rows on each data file page. If you have lots of concurrent inserters, they're going to be generating identity values for rows that are going to go on the same page. Only one thread at a time can be inserting into a page in memory. And so you see page latch underscore ex waits for specific pages, and you can dive in and see why that's actually occurring. And I'm going to show you that exact example in our first demo coming up. And then locking waits. Okay, so generally this is going to be some kind of contention issue, but it might not be locking itself that's the root cause. For instance, let's say that you've got synchronous mirroring set up on your server, and suddenly you see a whole bunch of blocking popping up. When a transaction is on a database that has a synchronous mirror or a synchronous AG replica, the transaction cannot complete and drop its locks until the final log block containing the commit log record for that transaction has been hardened on the mirror's log drive. So if that hardening process suddenly starts to take a lot longer, that means the transaction takes longer to commit, and so the locks are being held longer. That can manifest itself as sudden blocking. The problem there is not locking per se. The problem there would be maybe something on the network, or maybe something to do with the mirror server itself. Okay. So there's lots of information about what to do about blocking problems, so I'm not going to spend a bunch of time on this because we don't have time. Some information there for where to go looking. You might need to add non-clustered indexes. You might need to consider using snapshot isolation, especially if you're doing something, for instance, if you're seeing locking weights on a SharePoint system, because you can't change anything on SharePoint. You can enable snapshot isolation to work around some of the blocking and deadlocking issues that SharePoint has.
It'll work for anybody.
So let's do our first demo. Oops. So we're going to come in here. Now I've got 3 scripts here. The first one is my script to look at DMOS waiting tasks. I'm not going to run it yet because I have it scoped to only show user threads and there's not actually anything happening, but you can see that I'm actually joining it up with a whole bunch of other DMVs. Okay? Not just DMOS waiting tasks, and we'll see why I'm doing that when we get to running something in our demo. And there you can see it's auto-generating the URL for you to go and figure out what's going on. Now, I also have 2 copies of my DMOS wait stats script. And I've got 2 copies so that I can run part of the demo, zero out the weights, and then in the other wait stats window show you how the weights changed when the demo changes. Now, if I just run select star from DMOS wait stats, you can see we get 769 hours of output. I'm running on 2014, and there's not a lot of human actionable information here. Let's say I wanted to see my write log weights. I'd have to scroll all the way down till I find write log, and my server got rebooted this morning, so there's not very many happening. But to be able to see the average write log wait time, I'd have to take the average, the aggregate overall wait time minus the aggregate signal wait time, because SQL Server doesn't track the resource wait time, and then divide by the number of times that wait has occurred. So this is what part of what the script is going to do, is work out averages for us. Right? Now, there's this extra column, max wait time milliseconds, the maximum time that any thread has ever waited for this wait type. It's completely useless. Nobody ever uses it. You can ignore it. Okay? Now my script here, you can see it's doing some math to give you an ordered list of wait types, and it's filtering out a bunch of wait types that generally don't cause a problem. Okay. All of these wait types, they're just textual matches. This code runs all the way back to 2005, but you can see, for instance, this is a 2012 wait type that was added to do with indirect checkpoints. This all works because this is just textual matches against names of wait types. If I go ahead and run this query, this is the kind of output you're going to get. Okay. So in terms of most prevalent wait type descending based on this percentage. Okay. So we can see, and I'm not going to run through all this because this is just the server starting up, creating a database and so on. You can see how it's ordered. Now if I get this information for a real system, don't start down here. You start up here with what the most prevalent wait types are, because that's going to be most likely where you can make a big effect on the performance of your workload. Okay, so you're looking at the top 3 or 4 wait types, and eventually you might get down to here, but it's highly unlikely that you want to ever start all the way down here. So it gives us the overall wait times in seconds. These are the aggregates, and then it tells us the number of times it's been waited for, the percentage obviously, and then the average wait time in seconds. So for instance, this is 226.2 milliseconds. This one here is 0.8 milliseconds, and you can reorder the columns whichever way you want. This is just the way that I've always done it. And then there's that URL at the end. All right, so let's actually do something. So I'm going to run some code here. So just to show you what I'm doing, I've got a setup script that I'm going to show you. I'll run that. And then I'm going to fire up 200 clients. And I like to just use CMD scripts so that you don't have to download anything and install it. So when I click add 200 clients.cmd, it's going to run this guy 200 times, which will start a CMD window which does a SQL CMD of my client code. And at the end, I can just click stop test, and it gets rid of everything. Okay, so very simple setup. So let's look at my setup script first of all. Oops. So I'm going to create a database. Now obviously all my scenarios are contrived. They're also very, very simple, so you can see what's going on with the weight information rather than having to try and understand some complex workload. So I create a little database, and then I'm going to create a table that is going to have an insert hotspot. So I'm creating a table with just a single int identity column. That's obviously a very small row, And so there's going to be able to be 300 or 400 of those rows on any particular page. And if I start up 200 concurrent insert connections, they're going to be clashing. So they're all going to be wanting to insert onto the same page, and so only one thread at a time can do that, and we're going to see page latch EX waits. So I'll go ahead and do that. Over here, I'm going to flush out my wait statistics like this, and then I'll fire up my 200 connections. Like so. And if we go back up now and look at DMOS waiting tasks, if I run this whole script, here we can see some output. So we've got all the threads, all the SPIDs, with the thread ID, and thread ID is 0. If you only see that, that means there's no parallelism happening. Which scheduler it happens to be sitting on, how long it's waited so far, the wait type. This pops up when we've got locking. Right? The resource description, we'll come back to that. When there's parallelism, I'll show you that. When there's parallelism, I'll show you this. The database ID, you've got to be careful about this, because the database ID is the database where the code is executing, not the database that's being changed. And I deliberately set this demo up to do use master and then use 3-part naming to get into the hotspot database. So even though this says master, master is not the database where all these waits are occurring. And then the script gives you that URL, the graphical query plan, and the query text. And you can add whatever columns you want from all the various DMVs. Now look at this. Look at the pattern of waits here. Latch underscore EX. A couple of latch shares, but latch EX. This is a classic pattern that says insert hotspot, because look at the resource description. These are database ID, file ID, page ID. So there's an insert hotspot here. All these threads are all trying to insert into one of these 2 pages. Now you could go across to the graphical query plan and click it, and if it's a very simple query plan like this one, you're obviously going to be able to see, oh, it must be the hotspot table, right? But let's say that you've got lots of inserts happening, or maybe updates happening in various tables as part of your query plan. How are you going to be able to tell? So what you can do is go back over here and take this resource. So this is a database ID, and these 2, 1911, are a page ID. You go back over to my blog, and in that same wait statistics category, there is finding a table name from a page ID. So you take that page ID and you run the various queries that are in that blog post, and it shows you how to find your table name, okay, in that database. And then you can figure out why there's this insert hotspot happening on that particular table. So from waiting tasks, we can see there's a pattern we need to go and investigate. What about from wait stats? So I run my wait stats query, and sure enough, page latch EX comes out as the number 1, but only 2.3 milliseconds per wait. Is that something that I'm going to fixate on? No, probably not. So this information isn't enough for me to say, well, I've definitely got some horrible problem that's happening now. I could surmise and say there is, but I want proof. So I'm going to refresh about once every second and watch this wait count. So basically we're seeing 50,000 roughly page latch EX waits every second. That says to me that there's something going on, so I'm going to go and investigate. So sometimes from wait statistics you can see the problem, sometimes from waiting tasks you can see the problem, sometimes from both you can see that there's a problem. Okay. So now I'm going to make a change. I'm going to do this. And then over here I'm going to flush out my wait stats in my second window. Now that change that I made, if I rerun my waiting tasks script, it totally changed what's going on. And now we have locking waits. Okay, so we're seeing exclusive lock waits, okay, on all the threads apart from 1. And if we look at the resource description, it's one of 2 or 3 different pages. So there's another insert hotspot, but this is an interesting one because it's to do with page X-locks. And page X-locks don't happen naturally. They only happen if somebody specifically says with pagelock or paglock, however you want to pronounce it, on your query plan text, or if somebody has turned off the ability for an index to support row locks. So if I saw this particular pattern in waiting tasks, and I saw that it was page locks, I would first go and investigate and figure out which index is this happening on, and then I'd look at the query text. Is somebody specified page lock? And that could be something you want to do if you have a query that is causing lock escalation because of the large number of row locks. Okay, you can reduce the number of row locks by specifying take page locks, but you've got to be aware of some of the potential side effects of doing that. It's not something you're just going to go and do willy-nilly. And then I'd go and look, if the query didn't specify page locks, I'd go and look and see whether somebody did this. And of course I did this contrived scenario, right? So from waiting tasks, we can see there's a problem. And what about from wait stats? So in the second wait stats window here, right, now previously we had that, and after I made that demo change, now we're seeing this. So 100% of our waits are for exclusive locks. That's something that I want to investigate. But from wait stats, I can't tell the granularity or the lock resource that's being waited for. Waiting tasks, I can. Okay. So there's a couple of interesting scripts that you can use there. Any quick questions on that demo while I close it down?
Nothing on that demo.
Okie doke. I'm only going to take questions because I'm running a little bit long. I'm only going to take questions on the demos as I go along and do them, and then I'll stay and answer questions at the end of the session for as long as you guys have questions, and Steve can be bothered hanging out.
Okay, that'll be fine.
Because I know that some people do this over their lunchtime, and I want them to be able to get back to their work. So write log wait. You're going to see these on your server. Anytime that you have any changes happening to your database, you will see write log waits. That does not mean that you have a logging issue. You need to look and see how long the individual write log waits are for. And if the individual write log waits are for longer than your comfort level of write wait time, then you want to maybe do something about that. But you are always going to see write log waits. Okay? They don't mean you have a problem. If you're seeing write log waits happening, and you look at the average disk write queue length, and you're seeing that it's sitting at 31, 32 constantly for the log drive, then you're likely on 2008 R2 or before, where there was an architectural limitation, where there could only be 32 outstanding asynchronous log writes per database happening. If you have hit that, then you need to upgrade. Okay, 2012 and onwards, that limit's raised to 112. It's an awful lot harder to hit. I have seen people hit that though. Okay. So there's all kinds of things that you could do to try to alleviate write log waits if it is a problematic wait type for you. Probably the simplest one, and the one that I'm going to demo, is move the log to a faster portion of the I/O subsystem. That decreases the write log waits and makes them less of a performance component of your workload. Okay. Something that's very hard to do is you could actually make your transactions longer. Now, we as data professionals, we like our transactions to be as small and fast as possible. But every time a transaction commits, it flushes to the log. And so the more frequent, smaller flushes to the log are actually the worst case for log throughput. So our transaction throughput is actually kind of opposite to our log throughput. We want our log writes to be as far apart as possible and as close to 60K, which is the maximum log flush size, as possible. You could look to see whether you've got a whole bunch of log that's being generated that doesn't need to be generated. For instance, you have a bunch of non-clustered indexes that aren't being used. Every time those are maintained during regular inserts, updates, and deletes, that's extra log that has to be generated. Let me just take a quick drink of my water. All right. And then you might have fragmentation that's happening. Page splits generate a huge amount of transaction log. Other things you could try doing: implement delayed durability. So when a transaction commits, it doesn't have to flush to the log. I'll show you an example of that in a next demo. Or you could look at in-memory OLTP or Hekaton, and you could actually have no logging whatsoever. And we've seen some cases with clients over the last 6 months to a year where they're using that very successfully, maybe to remove temporary tables or to speed up ETL processes as well. Maybe even to speed up ASP.NET processing, because if you can make the ASP.NET session state tracking database in memory OLTP, that can have a huge boost to your ASP throughput. So let's look at write log waits. So I have a little USB drive plugged into my laptop, and I'm going to use it as G-colon. I'm going to use it as the I/O subsystem for my log file. It's not something I recommend you do in production because it's going to be really slow. And then I'm going to create a table called random data with identity column, a get date, some padding, and a couple of indexes. And then we're going to fire up couple of hundred clients and see what happens. So I'll flush out my weights here, fire up my 200 clients, and then let's go back and look at DMOS waiting tasks. Okay, now we've reached steady state. Now watch this. I re-execute, logging, 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 logging. Okay, we've got a logging bottleneck happening here. Okay, and we can see that this is all happening in database ID 9. And if we look, database ID 9 is going to be my hotspot database. So we've got a logging bottleneck happening there. And if we look at wait stats, we can see that write log is our top wait, and we're seeing an average of 74 milliseconds as our write time. Now, by anybody's standards, that is a very poor write latency. So I'm going to see what I can do to fix that. And the simplest thing I can do in the context of this is I can switch to a faster portion of the I/O subsystem. Hopefully Steve didn't just fall off his chair there. So I'm going to stop my test. And then I'm going to make a change. And instead of having G:, I'm going to comment that out. And I'm going to put my log on C:. So now I've got the data file on one of the SSDs in my laptop and the log file on one of the other SSDs in my laptop. And I'll rerun that whole setup script again to recreate that database. And then in this window, I'll flush out waits, fire up my 200 connections, like so. And if we go back to DMOS waiting tasks, we were seeing these high logging waits, so let's just execute that a few times. And we're seeing this pattern now. So we've got rid of our logging waits. Now, if this was a smaller user group, what I'd say to the people in the room is, okay, so what is this pattern that we've got now? So look at the pattern that we've got. Okay, and hopefully some of you watching on the meeting today are going to be saying, aha, that's the one we just looked at in the previous demo. It's an insert hotspot. Okay, because now we've got all these threads waiting for access to the same page. We've gone back to a classic insert hotspot. Now, if we look at wait stats, what we had before was 74 milliseconds. And now, if we look here, right, we're still got the same number of write log waits because our workload hasn't changed. In fact, we're going to have more of them because the workload's going faster. But now, our average write time, 0.3 milliseconds. Okay, because my SSDs are super fast. So that's more what I would expect. So we've still got the write log waits, but they're no longer a component of the workload that's slowing down the workload. Okay, very important to remember that about write log waits. Okay. So any quick questions, Steve, about that demo?
Hold on. No.
Okay, cool. So let's get rid of that. Now the other demo I want to show you around logging is I want to do a quick demo of delayed durability. So this was added in 2014. It's in all editions, and this allows you to say when a transaction commits, don't flush to the log. Right. So I'm going to turn delayed durability off. Now this demo only obviously works on 2014. My other demos will work all the way back to 2005. And I'm creating a contrived scenario where I've got this table where I've got these 9 rows, and my workload is going to be begin transaction, update random data, set C1 equals C1 plus 1. Okay, now C1 is not the clustered index column, that's C2. So it's able to do an in-place update of this integer. And what's going to happen is begin tran, xlock, 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 all the way down the rows, xlock on the row, commit tran. So no other transaction can be executing while this one is. So we're going to have a bottleneck waiting for this transaction to finish processing and flush to the log. So let me go ahead and add in perfmon. And I'm going to pull in from my database's performance object. Oops, where is it? There. I'm going to pull in the log flushes per second and also hit control transactions per second for my fast log file database. Now I can't use batch requests per second because each of my batches is an infinite loop. So we'll do that. Nothing happening right now. And I'm going to fire up 50 clients And then let's look and see what's going on here. Now I need to scale both of those down. And we'll look at log flushes per second. I'll highlight it by hitting backspace. It's going to turn black. Log flushes per second. We're doing about 12,000 per second. And I'll look at transactions per second now. It's exactly the same line because transactions per second is bottlenecked by the log flushes. Now watch this. I turn on delay durability. Check that out. So our transactions per second, the black line, doubled to 25,000 per second. The log flushes per second, the red line, dropped down to about 800, 900 per second. Okay? So if you have a workload that can benefit from it, then you might look at delayed durability. So if you're bottlenecked on log block flushing, delayed durability might help you. However, there is this small possibility that if the system crashes, you might think a transaction's committed, but if it didn't hit the disk, it won't be there after the system comes back up. So if you have a zero data loss service level agreement, you should not turn this on. Okay? And also, it's not something that's going to be effective for all workloads. It just depends on whether you are bottlenecked on log block flushing or not. So that's a very interesting feature that was added. Any questions on that demo, Steve?
This is a general question on this demo. Would you rather use perfmon or the scripts? I think the answer is it depends on the problem, but I'll let you answer that.
Yeah, it depends on the problem that you're trying to track. I mean, you can have perfmon sit there and track stuff in the background, and then you can analyze it using performance analysis of logs or Nexus or something like that. It really just depends on what your personal preferred performance methodology is. You might have a third-party performance monitoring tool that's also picking up some of this stuff as well. There's no real right answer to that, apart from make sure you are tracking things that will help you when you do have a performance issue.
That's it.
Cool. Thanks, Steve. Okay. So back to the slides. One more set of demos. We've probably got about another 10 minutes or so to go. Parallelism. Okay. So there are various operations that can run in parallel. Scans, for instance, and joins, join is the wrong word, junctions, let's say, between parallel zones in a query plan. So this is an example of one of those junction operators. This operator sits between two parallel zones of a query plan. And many people think that max DOP means your query won't use any more than max DOP threads. That is incorrect. Okay? Each parallel zone in your query plan can use max DOP threads. So you might have max DOP set to 8. Okay? For instance, my laptop, I might have it set to 8. And if I have a query plan that can have 3 concurrent parallel zones running at the same time, that would need 3 times 8 threads for those 3 zones, plus 1 for the control thread. Okay? Any particular operator, though, cannot use any more than 2 times max DOP plus 1. And the most expensive operator that does that, 2 times max DOP plus 1, is this one, repartition streams. Okay? So let's say we've got max DOP set to 4. For a repartition streams operation, we're going to see the control thread, which by historical accident is always thread 0. We'll see 4 producer threads, an exchange operator going out to 4 consumer threads. Okay, I'm simplifying, but this is what you need to know. So this is an example of a parallel operation. Now, CX packet, very, very misunderstood. At its very simplest form means you've got parallelism happening. So there's 2 things you need to think about. Number 1, you've got parallelism happening. Do you want parallelism happening? If you do not want parallelism happening for some particular operations, you need to prevent that. And I would not use max DOP to do that. I would use cost threshold for parallelism. We'll talk about that in the next slide, a couple of slides. The second thing you want to think about is if you have parallelism and you're okay with parallelism happening, is the parallelism good or bad? In other words, do you have a skewed distribution of work amongst your worker threads? That's bad parallelism. And you can easily see both of these using the scripts that I've been showing you. Okay. So as an example of good parallelism, let's say that we've got this table and we want to do a table scan of it, and we're happy with that being our query plan. So if it's a large table, we want that to happen in parallel. It's going to go faster. So with DOP4, we're going to have the control thread and 4 worker threads. Watch the threads 1 through 4. They each have the same amount of work to do, so they each take the same amount of time. Right? Now here's why CXPacket at its simplest form just means parallelism, because the control thread for any parallel operator will accrue a CXPacket wait until the end of the operator. So CXPacket just means you've got parallelism. Now here's where it could be bad. Now let's say we're doing a table scan again, but the statistics are now out of date. And so with the DOP4, the query processor thinks it's given the same amount of work to each thread, but in reality it's not. Thread 4 has got more work to do. Watch the black arrows. Thread 4's work takes an awful lot longer. So pull all those back together. Thread 0 is going to have a CXPacket wait till the end of the operation. If any other thread finishes well before the longest running thread or threads, they also accrue a CXPacket wait. So if you look in DMOS waiting tasks, and I'm going to show you this, if you look in DMOS waiting tasks and you ever see a thread ID other than 0 showing CXPacket, then you have a cardinality estimation problem, which is probably caused by out-of-date statistics. That is bad parallelism, and you need to get rid of that. So again, simple things here. You've got parallelism. Do you want it? And if you want it, is it good or bad? Okay. So the easy way to stop things going parallel is increase the cost threshold for parallelism, rather than messing around with max DOP. Cost threshold for parallelism is a number that's set to 5. It's a unitless number that says if the cost of a serial plan is estimated to be 5 or higher, create a parallel plan. Now, for a parallel plan to run, it has to gather the threads and resources, distribute the threads amongst the various schedulers, communicate between the various threads, and then tear down the threads at the end. So for a very small, tiny query, you don't want that to go in parallel. So you could bump up your cost threshold for parallelism. And in reality, the default should be higher than just 5. So you could set it to 25, 40, 50, whatever's going to work for you. Jonathan has a blog post there at that bit.ly link that will programmatically analyze your plan cache and give you a guesstimate of what you should set your your cost threshold for parallelism to. If you have bad parallelism, make sure your stats are up to date. If you're going to set max DOP, and you should have max DOP not set to the default of 0, either set it as a good starting point to 8, or if you have NUMA, figure out or find from your server admin the number of physical cores in each NUMA node and set max DOP to that. And then SQL OS will try to distribute the threads from your query within the cores of a NUMA node, rather than having them go to threads to schedulers all over the place. And that can help reduce threads having to communicate across NUMA nodes, and these are called foreign memory accesses, and they're very expensive. So that's why there's guidance about the physical cores per NUMA node. Now, I say set those two. Those are generalizations. You might want to experiment to see whether there's a better number, either higher or lower, for your particular workload. But 8 for non-NUMA and number of physical cores in a NUMA node are great starting points for what max DOP should be set to. So let's have a look at some parallelism, and then I've just got a couple more slides, and we are going to be done. So the first one, regular parallelism. This setup parallelism script creates a database with a single table, 100,000 rows with 1,000 columns, and random columns populated. And then what my script does is it does a set statistics time on, and then it declares 1,000 variables, and does a select top 10 from that big table of all the variables, so there's no output whatsoever, and then does an order by randomly generated column name with max DOP 8 and then a half-second delay. So I'm going to flush out weights here and then start that going. And we're going to look and see how long it takes. We're going to let it run for a few seconds. In the meantime, we'll look at waiting tasks. There we go. So here we can see what the script's going to look like when you've got parallelism happening. So we've got thread ID 0 showing CXPacket wait. We don't have any bad parallelism here because all the other threads don't show CXPacket. Now, whenever you see a CXPacket wait, it will be marked as blocking itself. That is by design. It is perfectly correct. Okay. So we're blocked because we've got an exchange happening, like I showed in the slides. For a CXPacket, my script will show you the node in the query plan where that's happening. So you can go across to the graphical query plan and click that and look at the node ID, and you can see where the parallelism is happening. Now, this is a very simple example. You might have a giant query with hundreds of things, and you can see where the parallelism is happening. And then it's also going to show you the degree of parallelism that that query is running at. Okay, so if you don't know what that is, maybe somebody's specified a max DOP query hint, for instance. Now all these other threads, not all the other threads, so all the threads apart from threads 2 and 6 are waiting for a latch, and that latch is controlling this data structure, access methods dataset parent. And this is a data structure to do with parallel scans. The threads basically get access to this and say, what's the next set of pages for me to go read? So if we look at our wait stats, we can see that we've got latch is one of the most prevalent ones. Not a big issue though, because the latch is such a tiny wait. And we've got a bunch of CX packet waits. So I'm going to say, oh my goodness, CX packet waits. I'm going to lower my max DOP. I'm pretending to be somebody that doesn't know any better. So we've got 41 milliseconds as the average resource wait. So let's stop this test. And here we're going to be able to see how long each one took. Now the first one always takes a long time as it populates the buffer pool. But now look at this, 400s, 500s, and there's my half-second wait. 400s, 500s, 400s, 500s, 400s, 500s. So now I'm going to knee-jerk and set my max DOP lower, thinking that it's going to help remove CX packet waits, which of course it will, but it's going to have a detrimental effect on our performance. So I'm just going to flush out the waits here, set that running. And so what we're going to start seeing here is how long each of the ones with DOP2 takes. 900, 900, 800, 900, 800, 900. So if we look at our wait statistics, we did manage to reduce the number of CX packet waits, but now each one is taking almost 200 milliseconds rather than 40 milliseconds. And we're seeing a consequent increase in our runtime. This is a query that needs things to be running in parallel because it's a large table scan. So don't knee-jerk with CX packet waits. Okay, figure out what's going on and decide whether to increase cost threshold for parallelism or whether you've got bad parallelism. So let's look at bad parallelism now. So I'm going to set this up. I'm going to show you what it's doing. And then I'm going to kick off 5 clients. If I look at waiting tasks, boom, look at that. Bad parallelism happening. Non-zero thread IDs waiting for CX packet waits. Okay, a whole bunch of them. Okay. Now, if we go and look and see what's going on, this is the query that's being run, just a select top 150. If I grab actual execution plan, execute this, look at the query plan, and look over here, look at properties, oops, and zoom in. So I faked the query statistics, the table statistics, and I said there are 10 million rows. Okay, and so it said, okay, I'm going to run in parallel. I'm going to give each of the threads 1.25 million rows to scan. However, the actual table only has 2,048 rows, so only one of those threads ends up doing anything, and all the rest of them are sitting there with a CX packet wait. That is bad parallelism. Okay, very simple example of that. And the way that I set that up was I created my table, and then I said, update stats, fake the row count, fake the page count. Okay, so a very simple test there. So, Steve, I'm going to hold all questions now till the end. I've only got a couple more slides to go so that we get stuff done.
Okay.
So, kill workers. So we're done with demos. A couple more slides. Async network I/O. The word that people fixate on here is network. This wait is actually SQL Server waiting for your client to respond to data that it just sent it. It's rare for it to actually be the network. It's more likely poorly written client code that's doing one row at a time processing called rebar, row by agonizing row, or maybe the client server itself, or the server the client's running on, just to be clear, has a problem. Maybe it's a VM that's running slowly, or the physical server has issues, whatever. It's unlikely, in my experience, to be the actual network. Okay, if you go to the client's server and ping SQL Server, it's likely that the ping time will be a lot less than the async network I/O wait. If the client server is running perfectly well and it's the client code, if you can't change the client code, there is absolutely nothing you can do about this wait type. It has nothing to do with SQL Server. It's pure client or network. If it is the network, then look for poorly configured NICs or something else wrong with the network. Maybe there's a bad switch or something like that. OLEDB we talked about. If your OLEDB weights are very tiny, 1 to 2 milliseconds or less, it's likely to be DMVs from a link server. Sorry, not from a link server, from a third-party performance monitoring tool. If it's larger, tens, hundreds of milliseconds or higher, it could be a link server or an SSIS package, something like that. If it's a link server and the link server is a SQL server, go across to that link server and do weight statistics analysis. If the link server is not a SQL server, I have no idea whatsoever what you should do, but I'm sure that there is some equivalent of weight statistics analysis that you can do on that RDBMS. And the last ones are the preemptive weights. Now these are really undocumented compared to everything else. I've documented some of them in my weights library. If you want to know what the preemptive OS weight is, take off preemptive OS and take whatever's left, space MSDN, and then go Google or Bing that, and you'll get the name of a Windows API, hopefully. I've already done that for you in all of the entries in the weight type library, but if you don't have access to that, then maybe that's what you could do. So to summarize, when you walk up to a server and you've been asked to do some performance analysis on it or figure out what the problem is, the first thing you're going to do before you touch the server at all is ask the people, what are the symptoms you're seeing? When did it start? What did you change? And once they've said, I don't know, we didn't change anything, then you start looking at weight stats. Okay, you're also going to look at other things as well, but make sure you've got weight statistics. So looking at DMOS weighting tasks, what's happening right now shows a pattern maybe. DMOS weight stats can maybe show a pattern. And remember, when you're looking at weight stats, the top 3 or 4 relevant weights. Don't start right down in the weeds. And if you're seeing latch underscore, then you're going to have to go and look at latch statistics on my blog, on the Pluralsight course, and so on. Now, whatever you do, make sure you make an informed decision about what you're going to do next. Don't just knee-jerk and say, this symptom must be this root cause. Okay. Some resources for you. There's, again, the link to the repository. There's a white paper that Jonathan and Aaron wrote back in 2014, which is a good, real beginner's guide to how to get stuck into weight statistics. There's a couple of other white papers. This one drops you in at 500 level. It's about 10 years old. A lot of the information there is not relevant anymore, so I wouldn't start with that one. I'd start with this one. If you want to go deeper, because I'm sure there are more advanced people out there listening to this, there's one on latches, one on spin locks that I helped to write, and then on my blog there's a lot of information that goes from kind of high-level weight stats all the way down into the guts of spin locks and how they work. And then, of course, there's the Pluralsight course. And with that, I am done talking, apart from questions. So, Steve, what questions do we have? I'm sure there are some.
Okay. In looking at active threads, what is a SPID -2? Is that an orphan transaction?
SPID -2 is a DTC orphan transaction. So you need to go to DTC and finish that transaction. I can't remember exactly how you do that, but if you go to my blog, I have a blog post about SPID -2, and they'll tell you how to go and figure that out.
Okay. Are T-SQL scripts available where we can capture the details similar to what WinDebug does for a SPID?
Yes. So what you can do is, if you go to, so basically, if you look at the stuff that I had on my in the weight stats library, where it shows you this is the call stacks. Okay. So you can get the call stacks. You can't get well, I guess you could follow what's going along. It would be incredibly slow to do that. The way you would do that is, you go across and you can say, you go to this one here, how to determine what causes a particular weight type. And I'll click on that. And you're going to end up using extended events. You have to download the symbol files for SQL Server, and I've got a blog post that shows you how to do that. You create an extended event session, and the extended event session is going to capture the call stack action, and that's going to be the SQL Server call stack. And then you turn on this trace flag, and it allows resolution of the call stacks. In other words, taking the call stack and pulling in from the debug symbols what the actual names of those various functions are. And then you're going to get stuff like this. Okay, so I've got this whole blog post that shows you exactly how to do that if you're interested. And incidentally, if you're somebody that's interested in helping gather information for that weight types library, this is what you're going to end up doing. Okay. Okay,
this one you may have answered just a minute ago, but they're in an availability groups environment running SP_who is active every 30 seconds, and they see some HADR underscore sync underscore commit wait types. If they increase, do I have to put any other options other than going to async?
Okay, so HADR sync commit is it's the equivalent of write log. Okay, so when you've got an availability group and a log flush happens, what happens first is the thread actually waits first for hadrosync commit, and then when the hadrosync commit comes back, it looks to see whether the local log flush has already completed, and usually the answer is yes, and so it's done. If the local log flush has not completed, because they happen at the same time, then the thread then also waits for write log. So hadrosync commit is basically write log for the remote synchronous availability group replica. If you're seeing the hadrosync commit waits increase, then it could be that you've got some kind of bottleneck happening on the synchronous replica. Maybe it's not able to cope with the volume of log that you've got going across there or something like that. And I think I might actually have information there. Oops, let's go to H. I might have information that says all that on my wait type library. Yep, so it explains what that is, and then it explains what to do. I don't have any call stacks yet, but it does tell you what to go do about it. Okay, so it's just as a generalization, if you have any issue with a wait type and you don't know what it is, check out the wait type library first, because as I said, I've done 298 of them, and if you can't, and every one of those has if you have a question, click here and it sends a question about that particular wait type to me. Because it might be something that I know about, I might be able to give you some advice, and I just haven't got around to doing that on the wait type library yet. Okay.
Okay. On the max stop recommendation, does that apply to ETL environments?
The max stop recommendation about 8 or number of physical cores in a NUMA node is a generalization across the board. However, as I said, if you have a specific workload that's running, not a more generalized workload, you might want to experiment with higher or lower degrees of parallelism. So it really depends what you're doing as part of your ETL, whether you might get a better answer or not. I mean, there's no more generalized guidance I can give apart from there's the general answer and do some testing to see what works best for you. Just like, saying something about, how many tempdb files or how many user database files should you have. Well, I can give you generalized guidance, but there might be your particular situation, a different number might be better for you. So I hesitate to say always use this number. Hopefully that answers your question.
In the scripts, is scheduler 0 indicative that a thread is waiting to be runnable?
No. This is the schedulers. So I've got 8 schedulers in my inside SQL Server for running my queries. They are numbered 0 through 7. It's a 0-based list. That's all.
Okay, the showed is great, but it's very reactive. Okay, when I come to the point. Okay. The stuff that we have here is reactive that we've looked at today. When I come to this point to look at wait stats, that I'm already in the situation where the customer has called in as worst case, can you give me a hint as to what to look for to avoid waits, except of course set up best practices?
You already hit the nail on the head. You should also be doing proactive performance monitoring, where you're looking at wait stats just over time to see whether performance problems are starting to happen. But in many ways, sometimes it is just some event that happens, like a query plan tips from one thing to another thing, and now you have some performance issue where you have no choice but to be reactive. You can't be proactive about absolutely everything, apart from be monitoring performance so that when something does go wrong, you can very quickly figure out what it is, or you might be able to see that something is starting to go wrong. I know, for instance, that in SentryOne's Performance Advisor, they will monitor some things and say, look, this is starting to get longer. You might want to go and look at what's going on here. Okay, so there are obviously proactive things you can do about that, but sometimes the nature of the beast is it's just reactive.
On the blog post that you wrote on creating call stacks, the reader wants to know is there something that tells you how to read the call stack? Is there a blog post somewhere on that?
Okay. So, for instance, you're looking at what does this stuff mean? Okay. There is nowhere that I know of that explains what all these things mean, but a lot of the names of these functions, because these are all C++ method and function names, are user readable. Okay, because the people that wrote the code have to understand what it is as well. To be honest, this is all query processor stuff. They use a notation called Hungarian notation, which makes things a little bit more difficult to read. If we look at one, let's look at a storage engine one. Let's look for let's do page IO latch share. Okay, so here's an example of one. So you can use your head to, without understanding exactly what's going on. Okay, so we're doing a query and we're getting a row. We're fetching the next row from a row set. We're on a heap and we're moving to the next page in a heap. And we've called down into the buffer pool to get a page. And now we're reading the page. So without understanding all of what these different things are, you can get at least some idea of what might be going on. If you have a call stack and you have burning desire to know what a particular thing means, by all means send it to me, and I can tell you what they mean, because I know what all this stuff means. But there is no, unfortunately, there's no documentation about what all this stuff means, because it's just basically the SQL Server code.
Okay, this user is talking about for DB locks timeouts on extents. May I ask if you have any materials or blogs regarding how to drill down for what is causing it and the queries that have timed out? Are there any DMVs to query them instead of using SQL Server profile or event block process report?
Well, the block process report would be something that I would recommend using, because it's going to tell you what the thing is that's holding the lock and what you're doing that's stopping the lock. You could also, when it's happening, you could look at the output from sys.dm_tran_locks for that particular resource to see who's holding it, who's waiting for it, and then you could see what other things the holder or the grantee is looking for. The description of the locks that the person's interested in is a little bit vague. If that person, if you're still online, if you want to email me with that question, I might be able to provide you some deeper information once I know exactly what locks it is you're looking for. Okay.
Okay, here's the last one. What's the relationship between hyperthreading and parallelism?
There's no relationship between hyperthreading and parallelism. What hyperthreading says is pretend that each processor has two schedulers, essentially. Well, make each processor have two schedulers, so that when you've got nothing happening on one scheduler, you can have threads running on the processor. It's just a way of being able to get better throughput for any physical processor core by having two essentially virtual cores on top of it. It doesn't really tie to parallelism, apart from you obviously have double the number of schedulers, so you might be able to get better throughput. In fact, that's the entire point of hyperthreading, is that you get better throughput because you can have more threads executing. Now, that could be all the threads are executing single-threaded queries, okay? Or it could be some threads are tied together running parallel queries, but there's no inherent tie between parallel queries and hyperthreading, if that's what the questioner meant.
Okay, well, there's a few more questions, but I'm going to have to run because I've got to go register my granddaughter for kindergarten. So.
Oh, cool.
Anyway, I really appreciate it. I love everything SQL Skills does for the community and for us. So thank you so much for a wonderful session. Thank you.
Thank you, Steve. Thank you, Steve, again. So anybody that didn't have their question answered, shoot me an email, and I'll do my best to answer for you, okay?
Okay. Thank you.
Thank you. Take care.
Bye.
Bye-bye, Nate.